All right, everyone, I've got a good lesson for you today. This is the age-old question of correlation and causation, and does correlation cause causation, right? Is there a causal relationship or some type of causal inference between variables, right? So just because we have a correlation doesn't mean we have a causation. So let's investigate these and see what shakes out here. I think it's going to be very interesting. So correlation is basically a linear association between variables, but doesn't imply causation. So if something happens, does something else happen or not? Okay, so one silly example that I heard, this is probably the canonical classic example of eating ice cream and shark attacks. So you'll see a big correlation between eating ice cream because it's warm in the summertime, at least in the Northeast. I live in New York City, so in the summertime it's warmer. People go to the ocean, they buy ice cream at the beach, they go swimming too, and sometimes people will get bitten by a shark. So does buying ice cream cause people to be bitten by sharks? No, of course not. There's no correlation. There is a correlation because of the heat, but one thing does not cause the other thing to happen, right? That's insanity, right? But there is high correlation, so you can see how these variables work, right? So you can have high correlation with no causation, or correlation. There can be an existing correlation and causation as well, right? So causation is basically analysis that shows insights between potential causal relationships. And again, if something happens, something else will happen. But is that just a an accidental causation, or is that a real causation? So let's take a look at this and see how we get along. So I'm going to import some data from the web here. We have the mtcars data set here. We have miles per gallon, cylinders, displacement, horsepower, weight, and acceleration. And we are going to look at the correlations between these variables, right? So here is the old-fashioned seaborn. I like seaborn. I like matplotlib, but I really like plotly, so I tend to use a lot of plotly because it's more dynamic, interactive. You can zoom in, you can zoom out. I can put my mouse over this plotly chart and you can see the results, and I can actually zoom in if I want to look at this in detail and then double click to zoom out, right? So you can see on the diagonal axis, it's always 1-to-1, right? Like if you're looking at the correlation of one thing, miles per gallon and miles per gallon, or cylinders versus cylinders, it's always going to be 1.0. That's a given, right? So if you see here miles per gallon and cylinders, you have a negative correlation because as the number of cylinders in a car increases from 4 to 6 to 8, the miles per gallon tend to decrease because you have more of a sports type of car, or it's heavier, just as a matter of fact of having more cylinders in the car from 4 to 6 to 8. The car consequently consequentially almost has to be more weight. I mean, maybe you can save money on fiberglass, maybe you can save weight on fiberglass or something like that. But almost universally, when you add more cylinders, you can add more weight to the car. And the displacement of the engine is going to have a negative correlation to miles per gallon, and horsepower, of course, right? As you increase horsepower from an economical um, type of car. I have a Volkswagen GTI. If I upgraded to a Porsche or to a Ferrari or Lambo, obviously the horsepower is going to increase significantly and the miles per gallon is going to decrease. I'm probably not going to do that anytime soon. But that totally makes sense to me. And as the weight increases, the miles per gallon decreases too, right? That's pretty much a given. That's what we just discussed. So we can see the correlations, and they're mostly negative here, although the weight and the horsepower have a high positive correlation, and the weight, whoops, I didn't mean to do that, and the weight and displacement have a pretty high correlation too. You see 0.93 horsepower to displacement, 0.89. So these totally make sense to me. That's why I picked this data set. I like it a lot. I've analyzed this in several of my videos. So let's look at the regression between weight and miles per gallon. So again, we're going to do a plot, and we can see here clearly as the weight of the vehicle increases, the miles per gallon decreases, and that totally makes sense to me, right? So if you have a Humvee or Hummer or whatever that thing is called, that's going to be a pretty heavy car. I don't even know how much the thing weighs, like 2 or 3 tons or something like that. I have a Golf GTI, it probably weighs like 2 tons. So as you increase the weight of the vehicle, the miles per gallon, almost without exception, is going to decrease, right? It just takes more power, more effort, more gasoline to move that vehicle, right? So let's look at the statistical summary of this. We have OLS. This is ordinary least squared regression, and you can see some of the metrics over here. So kind of strong R squared, like actually 0.70 would be statistically significant. We're just under that, and you can see these data points are kind of scattered around. So I would expect like a little bit tighter um, fit between the regression line and all the distribution of the data points. But we're not really getting that, but that's okay. It is what it is, right? And we have t statistic. So this is definitely significant. I think what was it, 2.9. I'd have to look at. Actually, I forgot. I think it's what's let me Google it. What is he? He significant. Oh, okay, that's fine. It's based on the number of features too, right? And I think we need like at least 30 to become significant. Two variables. Yep, we know that. We know that. Yep. But what's the number? I'm not seeing the number here. Okay. Degrees of freedom. Yep. Okay, that's fine. Oh, okay, okay. Okay, it's about two. I think a little over two. So we're there with the t statistic, and this is highly negative between the weight and what are we looking at? The weight in miles per gallon. Yep, and this is positive. So the constant. This is statistically significant positive, and this is statistically significant negative. Okay, so I think we're fine there. And then we're looking at confounding the variables. So we're looking at three different variables here, the weight, the horsepower, and the number of cylinders. We're fitting that into the OLS model, and we print the results, so that is fine. Everything looks fine there. We look at the intercept. That is where this red line is hitting the y-axis, so it looks like pretty much about 35, okay? So we have that, and we have a couple more variables, so now we have the constant, right? That is significant. This is, and this is weight and horsepower. This actually is not. I think it has to be, I think it's 2.96. I forgot. We just tried to look it up and I couldn't find it. I have to spend a little more time, but it's okay. I won't go down that rabbit hole too much. So all predictors are 0, 45.73. That comes from, where's that? Where's the 45? Oh, here's the constant, right? The constant coefficient. They're all set to 0. The weight of the car is 2.77, and the coefficient is also statistically significant, very low. So this exponent, negative exponent, so it's almost 0, right? This indicates that for every unit increase in weight, 1 pound, miles per gallon decreases by approximately this much. So every 1 pound added, the miles per gallon decreases, right? And we can see that from this other chart over here, right? So that is pretty obvious. And the number of cylinders coefficient is 0.389, which means that for every reducing miles per gallon by approximately 3.9, this coefficient increases 3.89. Okay, so it's rounding, so that's fine. And the standard error, we see it here, the t statistic is significantly different from 0, so we find some statistical influence here. The p-value is less than 0.05, which also is significant. So we want to see a high t statistic and a low p-value. For getting that, we know that our features are statistically significant. Okay, and I think we can wrap it up. I've got a couple more notes down here. You can read that for yourself. I'm not gonna spoon feed that to everybody, but I think we did. I think we covered this topic of correlation and causation pretty nicely. I'm trying to keep it kind of tight and kind of crisp here. I don't want to go down too many offshoots or too many tangents here. So I think that's it. We proved the point. I will post this code when I post the video a little bit later today, so you can copy and paste this for yourself and run it in your own Jupyter Notebook environment. So that's it, guys. Thanks for hanging with me to the end here. I think this stuff is pretty cool. I think it's very interesting. I want to put this code together here and then share my insights with you. So that's pretty much it. Gonna wrap it up. Thanks for your time today. Enjoy the rest of your day. Goodbye.